Welcome to the Deep Dive, the show that takes a huge stack of specialized research and delivers the absolute essential knowledge directly to you. Today, we're diving into a question that really changes how we look at one of the world's most critical professions. We're asking, is writing software just a cognitive 9-to-5 job, or is it actually a craft? A physical discipline that demands the same kind of, rigorous, deliberate practice we associate with a concert pianist or an Olympic athlete?
It's a fantastic question.
Yeah.
Because most people, and a lot of people inside the industry, they see coding as purely a desk job, just a long series of logic puzzles. But the material we've dug into today, it treats software development as something much more
Physical.
a discipline that needs muscle memory, that needs instantaneous response, a kind of fluency that you can only get from really formalized practice.
Exactly. And our mission for this deep dive is to explore the surprisingly short history of formal software practice, which, spoiler alert, wasn't really a recognized idea until after the year 2000. We're going to trace its evolution and focus on how the world of martial arts became kind of the definitive blueprint for modern programming mastery, giving us this whole concept of the coding dojo.
And that timeline, that's what our sources call the practitioner's paradox.
The practitioner's paradox.
Yeah, you'd think that practice, just trying something to get better at it would have always been a part of programming. But the formal, recognized discipline of practice, that's a very, very recent thing.
Okay, so let's start at the beginning. The initiation ritual for basically every programmer, the first practice program.
Yes.
I'm talking about that one function that proves, without a doubt, that you can write code, you can compile it, and you can get it to run in whatever environment you're in.
The famous hello world sent function. It seems so simple, but it's just profoundly important. The sources all point to it, popularized on page 6 of the C programming language KNRC from 75. And its purpose is just that. It's foundational. It doesn't matter if you're setting up a massive build environment or learning a brand new language, assembler, basic, you name it.
If you can print hello world, you're in business. You've got a working foundation.
You're off the ground.
So it's the ultimate benchmark. But before that became formalized, back when this practice culture just didn't exist, what were early programmers doing that served the same purpose?
Oh, there are some great stories there. Back in the late 60s and 70s, one of the first things you'd write on a new machine was something called squint.
Squint.
The squares of integers. Just a tiny loop to prove the arithmetic logic unit actually worked.
Mm-hmm.
Then later, in the personal computing boom of the 80s, people would write these little basic programs.
I think I remember this.
Right. They'd print these continuous streams of characters like V's and slashes, just filling the screen in these complex patterns. It looked super cool, but the code itself was maybe 4 or 5 simple lines.
So those were practice programs in a modern sense. They confirmed the machine worked, the syntax was right.
Technically, yes. They were proof of execution. But here's the crucial distinction, and this is the paradox. Programmers back then did not see it as practice. They saw it as a functional test. A test of the hardware or the compiler.
Not a test of the programmer.
Exactly. The idea of dedicating time just to improve the human efficiency of writing the code was completely foreign. I mean, we were using punch cards, teletypes. We didn't even get screen editors until the late 70s.
So if you were spending hours, maybe even days, waiting for a single result,
Right.
your motivation wasn't about being fast or fluid. It was just about getting it right. It was survival.
Precisely. The whole process was defined by this just glacial speed. The goal was to optimize the machine's time because that was the precious resource. Today, the game is completely, totally flipped.
Okay, so if the code itself hasn't really changed that much, we're still using assignments, if statements, while loops.
The basic building blocks, yeah.
What on earth happened with the technology that suddenly made practice not just a good idea, but mandatory for a professional? So let's unpack that shift, because this is where the physics of the computer really changes the sociology of the profession. We have to talk about what our source material calls the 22 zeros.
The 22 zeros.
Yeah. This isn't just a small improvement. This is like rewriting the laws of physics for computation.
To get this, you have to ground yourself in the past. You have to compare machine today to the quote-unquote powerful machine of its day.
Let's do it. What are we looking at?
Let's look at the PDP-8i. This is from the late 1960s.
Okay, give us the specs on that beast. The machine that changed the world.
Well, it was a marvel for its time, but compared to now, it's just It's unimaginable. It had a cycle time of 1.5 microseconds,
Microsecond.
had 4,096 12-bit words in its core memory. That's barely 6 kilobytes of usable memory.
Wow.
Physically, it was the size of a refrigerator. It ate up huge amounts of power. And the main way you talked to it was a 10-character per second teletype, just clacking away.
And storage. A disk drive.
A huge spinning platter that stored maybe 32K of 12-bit words.
Okay. Now let's compare that to the machine referenced in the source. A
Yeah.
laptop from around 2010, a MacBook Pro. And even that comparison is what, over a decade old now?
And even then, the difference is just absurd. That laptop has a 2.8 gigahertz dual-core processor, 8 gigabytes of RAM, a 512 gigabyte solid-state drive.
And it fits in a backpack.
Fits in a backpack, sips less than 85 watts of power.
The physical difference is one thing, a fridge versus a backpack. But it's the sheer computational power where you get that aha moment. We really need to walk through the calculation here.
Let's do it. Let's just break down the factors of improvement. The processor is 8,000 times faster.
8,000, okay.
It has 2 million times more offline storage
2 million?
and 16 million times more memory.
That's already getting hard to picture.
And we haven't even gotten to the other factors. It takes up, what, 1% of the physical space?
Consumes 1% of the power.
And in constant dollars, it's about 1/25 of the price.
Okay, so if you multiply all of that together.
This is where the number just becomes incomprehensible. 8,000 times 2 million times 16 million times 100 times 100 times 25. You get 6.4 times 10 to the power of 22.
22 zeros. 22 orders of magnitude. That's the difference in what we can do technologically. And you can't even grasp it.
You really can't. The usual analogies like angstroms to Alpha Centauri, they just don't work. We need something more relatable.
Okay, give it a shot. How do we make that number make sense?
All right, think of it this way. Imagine you gave a PDP-8i a really complex problem to solve, and you started it running the moment the Great Pyramids in Egypt were completed.
So thousands of years ago.
A modern laptop, given that same exact problem, would have finished its work about 4 months ago.
Wow. Okay. That puts it on a scale of human history. The difference isn't just big, it's civilization-level transformative.
Or think about data storage. If you wanted to store just a single day's worth of YouTube uploads on those old PDP-8i disk drives.
Just one day of cat video.
Just one day. You would need a chain of those disk drives stretching from the Earth almost all the way to the sun. That is the 22-0 difference.
So that brings us right to the synthesis point, the huge question. If the technology has changed that much, but we're still writing if statements and while loops,
The same fundamental logic.
what does all that power force us to do differently?
The change isn't in the instructions we write. The change is in the cost of iteration, the cost of getting it wrong.
In the old days, computational time was so scarce, so slow.
You'd spend 99% of your time just thinking. Perfecting the code on paper, you had to get it right the first time because the penalty for being wrong was huge. You were optimizing for the CPU.
And now?
Now we have effectively infinite, cheap, immediate CPU time.
So we optimize for human time.
Exactly. A programmer's hour is infinitely more valuable than a CPU cycle. The technology has made iteration so fast, so effortless, that the job has changed from get it perfect on paper to iterate perfectly at machine speed.
And that incredible velocity. That's what makes practice mandatory.
You need practice just to handle that speed without crashing.
The barrier to entry moved from just thinking correctly to executing correctly at speed. And that link between all that power and the need for practice, it's all captured in this idea of turnaround time.
Right.
The 22 zeros are what enable the kind of speed that forces coders to develop muscle memory.
And you can see it in the history of the compile test loop. I mean, it's a history of pure acceleration.
So we start in the 60s.
In the 60s, waiting a day, maybe 2 days, for your compile results was normal.
A day or two.
Yeah. Then you move to the late 70s, 80s. A big 50,000-line program might take 45 minutes to compile.
Okay, that's a coffee break. A long coffee
A huge mental break.
Yeah.
The penalty for a mistake was still high, and it was slow. You had time to context switch.
But today, programmers just don't wait. We have these amazing tools, continuous integration.
Right. The sources mentioned this 64,000-line Java project. A full build, including all the unit integration tests, runs in under 4 minutes.
4 minutes for full quality assurance. That's less time than it takes to pick a song to listen to.
And that's the full build. The actual creative loop, the test-driven development cycle, is even faster.
The red-green refactor loop.
Exactly. Running a small set of unit tests takes seconds. which means a skilled developer can spin that compile test loop 10 times in a minute.
10 times a minute.
Think about that, 10 chances to check your work, to refine it, to iterate every 60 seconds.
That velocity, it changes the programmer from a thoughtful planner into a reactive performer.
Yes. And that's where the martial arts analogy really comes in. The sources are clear. Going fast is productive, but only if you have the practice to back it up.
It's the paradox of speed. It's not about being reckless.
No, it's about making instantaneous decisions. You have to recognize a situation, a compiler error, a design problem, a failing test, and know exactly what to do about it, all within milliseconds.
Okay, so let's use the combat scenario. Two martial artists are fighting. They don't have time to, sit and analyze the physics of a punch.
Of course not. They recognize the attack, and their body responds subconsciously. It's a primal, instant reaction, a perfected movement. And that frees up the conscious mind to work on the higher-level strategy. Where do I strike next? How do I end this? The trained reflexes handle the low-level details.
So the connection to coding is, if you're spinning that code test loop 10 times a minute.
You have to train that same primal part of your mind. Your muscle memory has to recognize the red bar and execute the fix in milliseconds.
Because if you have to stop and think.
If you pause for 5 seconds to look up a keyboard shortcut or to remember the syntax for a refactoring, you've broken the flow. You've crashed the cycle.
So by practicing the low-level execution, the typing, the commands,
you free your conscious brain to focus entirely on the hard part. The architecture, the business logic, the actual problem you're trying to solve.
That makes perfect sense. It's about getting the low-level mechanics out of the way of the high-level thinking.
The guitarist analogy, like Carlos Santana, is perfect here.
Right.
Santana isn't thinking, okay, index finger, fret 7, B string. No. He hears this complex melody in his head, and his body just translates it. The finger motions are completely autonomous.
And that only comes from one thing: deliberate, endless practice. Scales, etudes, chord changes.
Exactly. The coding equivalent of those practice exercises.
And if you want to spin that loop 10 times a minute, you need that same level of fluency. Your hands, your judgment, they have to be practiced enough to keep pace with the machine.
If you're struggling with which keys to hit, you're asking your conscious mind to do two impossible things at once: invent the melody and figure out how to play the guitar.
So this explicit need for an instantaneous practiced reaction, which sounds just like the training of a martial artist, leads us directly to the idea of the coding dojo.
The dojo is the structured space for this kind of deliberate practice, and it often centers around test-driven development, or TDD.
Let's connect that back to the speed we were just talking about.
Yeah.
TDD runs on the red-green refactor loop.
Right.
Red, you write a test that fails. Green, you write the absolute minimum code to make it pass, refactor. You clean up that code, and the test makes sure you didn't break anything.
Exactly. And that loop is the perfect high-speed feedback mechanism. It keeps you taking these small, safe, incremental steps. The dojo is really about formalizing how to do that loop with the most efficiency possible. The goal is to make red-green refactor as unconscious and fluid as breathing.
And the most famous example of this, the one that really showed the whole community what this looked like, is the bowling game Kata.
The bowling game Kata is absolutely foundational. Robert C. Martin wrote about it in his book, Agile Software Development, way back in 2003. It's just a beautiful little problem. Calculate the score of a bowling game. It only takes about 30 minutes, but it's famous for pushing you through these subtle design problems and toward a really elegant solution.
So seeing that Kata demonstrated live, that was the moment people realized what deliberate practice could look like for a programmer.
It was a huge moment.
Yeah.
But the formal idea of the coding dojo, as a place where people get together to practice, that came a little later.
Right. Our sources say that was really established at the XP 2005 conference in England.
Yes, by Laurent Bossavet and Emmanuel Gaillot. They basically proved that programmers could gather in a room, open their laptops, and just practice technique together without worrying about shipping a product.
And the core exercise inside the dojo is the kata. We should define this really carefully, starting with the martial arts definition, because the programming one is a direct reflection.
In martial arts, a kata is a precise, choreographed sequence of moves. It's like a simulated fight. The goal isn't to win because there's no opponent. The goal is to perform the movements until they are perfectly fluid, biomechanically efficient, and instantaneous.
You're trying to get infinitesimally closer to perfection with every single repetition.
Exactly. The movements become automatic, so when you're in a real fight, you don't have to think about them. Your mind is on strategy.
Okay, so now translate that to programming.
A programming kata is a precise set of choreographed keystrokes, hotkey combinations, and mouse movements that simulates solving a programming problem.
And the crucial distinction here is that you are not trying to solve the problem.
No, because you already know the solution. You're
Yeah.
practicing the movements and the decisions that go into implementing that solution.
So with the bowling game kata, if you've done it 20 times, you know exactly how the logic for a strike or a spare should work.
Right. So on the 21st time, you're not thinking about the logic. You're thinking about your hands. Did I use the hotkey to extract that variable? Or did I waste time scrolling and clicking with the mouse?
It's about micro-optimizing the physical interface between you and the computer.
Yes. You're training your brain and fingers to react instantly. And by doing that, you start to discover these subtle efficiencies in your movements, which, surprisingly, often leads you to discover efficiencies in the code's design itself.
When you do the same kata over and over, you're driving those common problem-solution pairs deep into your subconscious.
So when you see that pattern in your real work, your fingers already know the keystrokes. Your mind already knows the refactoring to apply. You just skip the whole deliberation phase.
And just like a musician needs a whole repertoire of exercises, a programmer should have several katas that they practice regularly.
Absolutely. The sources list the bowling game, prime factors, and word wrap as the canonical examples. They're simple enough that the logic doesn't get in the way, but complex enough to force you into making real design decisions.
I read one source that suggested a great goal is to perform a kata so flawlessly, using only hotkeys, that you could set the keystrokes to music.
That's the definition of mastery, total fluidity. And the dojo isn't just about solo practice, that martial arts framework. It also gives us these really effective ways to practice in pairs and in groups.
Right. Let's start with Wasa, the paired routine practice.
So in jiu-jitsu, Wasa is when two partners memorize a routine and just play it back. One person attacks, the other defends. They do it over and over, focusing purely on perfecting the form and the motion. Then they switch roles. The outcome is known. The goal is technical perfection.
So how does that translate to two programmers at a keyboard?
It maps directly to a game we call ping-pong pair programming, but structured as a Wasa.
So in normal ping pong, one person writes a test, the other makes it pass, then they switch. But with Wasa, there's a higher level of critique.
Exactly. The pair picks a standard kata, like prime factors. Partner A, the aggressor, rates one unit test that targets a specific known part of the solution. Then partner B, the defender, has to make that test pass, but they have to do it following the established optimized movements of the kata. Then they switch.
So the focus isn't just, did the test pass, it's how did you make it pass?
Precisely. They're critiquing keystrokes. Partner A might say, hang on, you reach for the mouse to rename that? You need to use the rename symbol hotkey. It's 2 seconds faster and it keeps you in the flow.
It's this micro-critique of the physical movements that enables that high-speed loop we were talking about.
I love that. And our sources mentioned a really cool competitive twist on Wasa, too.
Yes, when the pair chooses a new problem instead of a known kata.
The game becomes a test of skill under pressure. The programmer writing the test gets to control the nature of the challenge. Well, say you're building a simple parser. The test writer might write a test that forces the other person to use recursion. Or maybe a test that demands they solve it with a really strict memory limit.
So the test writer becomes the aggressor who dictates the style of defense. It's not just about finding a solution, it's about showing you've mastered a specific implementation style.
It introduces this element of competitive discipline. You're challenging your partner's fluency in a specific technique, making sure they can execute it flawlessly, even under pressure.
Okay, so that's paired practice. Now let's move to the free-form group challenge, Randori.
Right. Randori in martial arts is free-form combat. It's about setting up complex, dynamic scenarios. Maybe it's one person defending against two attackers. It's open-ended.
Simulated combat doesn't map perfectly to coding, but the spirit of a dynamic multi-person challenge definitely does.
And programming Randori captures that perfectly. It's basically a multi-person, two-man Wasa, but with a big twist. You're solving a new problem that nobody has solved before.
And the key mechanic is the constant rotation and the shared screen.
Absolutely. The code is projected up on a big screen for everyone to see. One person walks up, writes a single unit test, and then immediately sits down.
And the next person in line has to.
The next person steps up, has to make that test pass, and then write the next feeling test. And it just cycles around the table, fast. The constant change of control means no single person owns the design. It emerges from this collective, high-speed reactive process.
That sounds incredibly difficult. You'd need immense focus and the ability to get up to speed instantly.
It forces you to adapt. You have to understand the entire state of the code base in the 2 seconds it takes to sit down and read the test that was just written. It's the perfect training for high-pressure, collaborative work where you're constantly dealing with code written by a dozen other people.
So just to sum up the training regimen, Katas build your solo fluency, Wasa perfects your low-level execution with a partner, and Randori trains you for high-speed, collective, adaptive problem solving.
And all 3 are a direct response to the need for speed that was created by that 22 order of magnitude increase in computing power.
Okay, so we have established the how of practice. Now let's shift to the what. Our sources really emphasize that professional programmers face a unique risk. The work itself can force an unhealthy narrowing of your skills.
This is such a critical point. It's like a silent killer for long-term careers. If your job is to solve problems using Java and the Spring framework for a bank, day in and day out, that's all you get good at.
Which is great for your employer's immediate needs.
Right. But if you only rely on your job to develop your skills, your resume gets narrower and narrower. You become extremely vulnerable when the technology inevitably changes.
You become a specialist in a stack that might be obsolete in 5 years, and your fundamental broad programming skills just kind of wither away. So how does a programmer fight that?
The first solution is very concrete. Contribute to open source.
This is like the programmer's version of a lawyer doing pro bono work.
Exactly. You're dedicating your professional time to a project not for money, but for skill expansion. It's the best way to force yourself out of your comfortable silo.
So if your day job is Java, find a Rails project to contribute to. If you write C++ for finance, find a Python data science project.
You deliberately expose yourself to completely different languages, different architectures, different ways of thinking. These are insights about memory management or functional programming that you would never, ever encounter inside the strict walls of your corporate job. It's career insurance.
Okay, so that brings us to the second strategy, and this one is maybe the most controversial, the idea of practice ethics.
Yes.
Our sources make a really stark, ethically charged claim here that professional programmers must practice on their own time.
Yeah.
That it's not the employer's job to keep your skills sharp.
No, hold on. That sounds like a really heavy burden. I mean, in a world where we're all talking about work-life balance, is it really reasonable to expect someone to work a full week and then go home and code more for free?
Why is that ethical mandate stronger for a software developer than, say, an accountant or a teacher?
It's a fantastic question. And it really gets to the heart of defining what makes something a profession versus just a job. The argument is that this mandate is stronger in engineering and craft professions because the pace of change is so much faster and the stakes of incompetence are higher. The core argument rests on a few key analogies.
Okay, lay them out for us.
Well, think about it like this. Patients don't pay surgeons to practice tying sutures on the weekend.
Right.
Football teams don't pay their players to run through tires in the off-season. And concertgoers don't pay a world-class musician to practice their scales before the show. The expectation is that the skills you bring to the performance, the thing you're being paid for, are already perfected.
I see. So you're hired because you are already good. You practice to stay good.
Precisely. You wouldn't hire an architect who only starts learning their design software when they show up at your office. Practice is the non-compensated investment you have to make to maintain the highly compensated skill. If your skills get rusty, you're actively diminishing the value of the time your employer is paying for. The employer pays for performance. The employee is responsible for readiness.
So the ethical mandate is that you owe it to your profession and really to yourself and your own career to maintain that competitive edge independent of what your boss asks you to do today.
And that leads to a very specific rule for how to practice. Since this time is your investment in yourself, you have to maximize its value through diversity.
Meaning you should actively avoid using the exact same languages and platforms that you use at your day job.
Yes. Keep those polyglot skills sharp. If you work in a .NET shop all day, then your practice time, maybe it's 30 minutes at lunch or an hour at night, should be dedicated to practicing Ruby or functional programming in Haskell or contributing to a Go project.
Because your employer benefits when you bring a high-level, broad understanding of programming in general.
Absolutely. By practicing outside your domain, you learn how other people solve problems, how other languages handle complexity. That versatility makes you a much better problem solver in your main job, and it ensures you're valuable no matter which way the technological winds blow. It's the ultimate form of professional self-reliance. So we've established that this 22 order of magnitude increase in computing power has completely flipped the script on programming. It's transformed it from this slow, paper-based mental exercise into a high-speed, physical craft. And knowledge is only really valuable when it's so deeply internalized that you can apply it instantly.
We've seen how modern coding really demands the same kind of dedication as martial arts, requiring us to gain this fluency in keystrokes and response patterns and in high-speed decision-making through these very formal techniques like Katas, Wasa, and Randori.
Right.
These techniques, they aren't designed to teach you what to solve, but how to execute that solution with something approaching perfection.
And in the end, the professional mandate is pretty clear. Whether you're a programmer, a doctor, a musician, or an athlete, all true professionals practice on their own time. They realize it's their responsibility, not their employers, to keep their skills sharp. Practice is the investment you make in yourself when you're not on the clock, to ensure that when you are on the clock, you're delivering the highest level of performance possible.
So we'll leave you with a final thought to think about. If you see coding practice as something you only do when you're clocked in, are you treating it as a transactional job? Or are you embracing the responsibilities and the rewards of a true profession?
And what is the one skill, the one new language, or the one challenging kata outside of your current stack that you are going to commit to mastering through dedicated daily practice? How will you ensure your fluency keeps pace with the exponential power of the machines you command?
Figure that out, and you'll find yourself moving from just writing code to truly mastering the craft. Thanks for joining us for this deep dive.